Well, it's fantastic to be presenting to you tonight as part of this event. My name is Dave Howey. I run a research group in the department that's focused on modeling and control of battery systems. And in this short talk, I'm going to give a quick bit of background context on where we're at today with batteries, and then a bit of an overview of our research, and I'll touch on a couple of things that we've been doing recently. So first, let's take a quick look at the history of electrochemical batteries. Apparently, it was Benjamin Franklin who, in the mid-18th century, first used the term battery to describe a set of capacitors, actually, so not batteries at all. And these were called Leyden jars. You can see a picture of them on the screen here. They were glass coated with metal surface on each side, and they were charged by a static generator. It has been speculated that actually a device was invented in antiquity called the Baghdad battery. There's a picture of it here on the left, although it's not quite clear whether it was a battery or not. In 1780, in a slightly Gothic experiment, Luigi Galvani was dissecting a frog attached to a brass hook. And when he touched the frog leg with his iron scalpel, the leg twitched. And Galvani thought that there was energy that drove this, which he called animal electricity. But he chatted to his fellow scientist and friend, Alessandro Volta, and Volta disagreed. And Volta said, it's probably just two different metals connected by some kind of moist intermediary. And Volta was correct. And in 1800, he invented the first battery, as we might call it today, which became known as a voltaic pile. You can see a picture there on the screen. So this was consisted of a stack of copper and zinc discs with a brine-soaked cloth in between. And this had a huge advantage over the Leyden jar because it could keep charged for a long time. It could deliver a continuous and stable current. So it became very useful, and lots of initial electrical experiments were conducted using these types of piles. Batteries have come a long way since then. The lead acid cell was invented in 1859. And if we fast forward to the 1970s and 80s, the foundations were laid for the invention of the lithium-ion battery. And in fact, the cathode material for lithium-ion was invented right here in Oxford by John Goodenough and his colleagues. And as a result, Goodenough and his other colleagues, Whittingham and Yoshino, won the Nobel Prize for Chemistry in 2019. So why is the lithium-ion battery so revolutionary? Well, in terms of performance, it offers high energy density, good cycle life, and high power density. Energy density is up to about 700 watt-hours per liter at the moment, and these batteries can last thousands of cycles. So what has this done? Well, it's basically unleashed a revolution in portable electronics, and it's currently driving a huge switch to electric vehicles. And you can see in this graph here, as production has increased, basically the price has dropped radically. So this shows what we call a learning curve. So you can see we started at a very high price, over $6,000 per kilowatt hour of batteries. Today we're heading towards $100 per kilowatt hour. To put that into context, if you went out today and bought an electric car such as the Kia e-Niro, it has a 64 kilowatt hour battery. If you bought that in 1991, that would have set you back perhaps $500,000 or something like that. So we're in this truly sort of interesting time where prices have come down massively. And the question is, what's going to happen next? So here's a projection from Bloomberg, which shows some ideas about how battery production might ramp up over the next 15 years. And the production levels are truly eye-watering. So today we're at about 100 gigawatt hours of production per year. And if we fast forward to 2035, we're approaching almost 5 terawatt hours per year of battery production. What's interesting is most of that is dominated by passenger electric vehicles. And a lot of that has been driven by demand in China. Of course, there are really important issues associated with this. So where do we get the materials from to make these batteries, and what happens to them at end of life? And unfortunately, I don't have time to go into those issues in huge depth, but I just want to acknowledge that they are important issues, and there's a lot of research being done on those issues. So if you want more info, have a look at the excellent insights that have been produced by the Faraday Institution, which are freely available on their website. Where does our research fit into this? Well, batteries are a lot like people. They want to be at a comfortable temperature. You don't want to get too hot. If you go to very high temperatures, then you have issues with safety. If you go to very low temperatures, you have issues with high internal resistance and trouble with charging. So you want to be at a comfortable temperature, similar to the temperatures we like. Batteries are mechanically quite fragile. They need to be packaged correctly, and they don't want to be punctured. And finally, they degrade over time, sadly, and eventually they die. So these graphs here show how, for example, the charge-discharge voltage versus time curve changes as you cycle the cells. So after 1,000 cycles, you can't get quite as much charge into the cell as you originally could. And so we can represent this as capacity fade. So it's a bit like the size of the fuel tank in your vehicle decreasing over time. And it might seem quite dramatic, but actually these effects, if you look at the y-axis, are relatively modest in most cases. So in the next few slides, I just want to give you a few examples of how our research in my group fits into this. And I'll first highlight some work on thermal modeling, and then I'll talk in a little bit more depth about modeling of lifetime and degradation. So how does modeling and simulation help us? Well, it can help us to understand the key factors that impact the behavior of batteries. And here's an example of some work that's been being done by one of our postdocs, Jay Lin, who's extending some research that was first begun by my colleague, Charles Monroe in the department and his team. So if you take a battery, this one is a 20 amp hour lithium-ion cell. It's called a pouch style cell. It's about the size of an iPad. And you point an infrared camera at the cell while you're charging and discharging. You'll see that a hotspot starts to form in the middle. It's not that dramatic. You can see this temperature scale is fairly compressed. And as we cycle the battery, we'll see a few interesting things happening with the temperature. So here what we're doing is going to a state of charge and then cycling around that state of charge, perhaps plus or minus 5%, something like that. So you can see these voltage swings. You can also see that the battery warms up, driven by a sort of RC time constant. And you can see these wiggles on the temperature as well. And these wiggles are quite interesting because they're actually caused by entropic effects, reversible heating and cooling. I'll just show you a quick video. So this video compares experimental imaging of the temperature on the left with a simulation. So if we turn that on, you can see that gradually the hotspot grows towards the top of the cell where the tabs are connected, and it slowly moves down. And you can see as we charge and discharge, you can see this almost breathing kind of effect caused by these entropic temperature changes. It turns out that this kind of exercise actually gives us a lot of information about what's going on inside a battery. And in fact, if we take a cross section through the temperature profile along the horizontal plane in this picture, then the curvature of the temperature profile is strongly impacted by the diffusivity of the transport of lithium in the graphite. And that's what this picture up on the top right shows. So modeling can help us to understand the factors that drive performance. And in this case, if we want to capture the hotspot position and temperature accurately, we need to couple an energy equation into the model, and we need to model ion transport, particularly in the negative electrode well. In terms of impact, industry can use these kind of models to design better thermal management systems, for example, maybe to remove heat through the copper connections to the cell rather than through the surface. So that's thermal modeling. Another crucial aspect of performance, which I want to dive into for the next few slides, is how to predict degradation and lifetime of batteries. And this is a really important issue, especially for large-scale systems. For example, if you connect a container full of batteries to the grid, then that's a 10, 15, 20-year project, and lots of money is involved. And you want to make sure that the warranties and the insurance and all the finances are lined up, and the battery life is a strong factor in that calculation. So there are two main approaches that I want to briefly review. The first one, which you can see on the screen, is what I would call a physics-based approach. So the idea here is to try and understand and model all the relevant things that are driving the battery degradation. So for example, in this cartoon, you can see a few different things. And this is not completely comprehensive, but you can see some electrochemical effects like lithium plating, growth of something called the solid electrolyte interphase, which is a kind of passivating layer on the surface, and then some mechanical things like cracking and pore clogging. So all of these things kind of happen, and gradually the battery's capacity fades over time and its resistance increases. And we could try and put together equations to model all of these different mechanisms. And these models can become quite tricky to solve with lots of parameters. It can take some computing power to make this happen. But if you could get it to work, then you've got a truly predictive model of what's going on, and you can use that to look at lifetime in different applications. An alternative approach is what I would call a more empirical data-driven view. Take the data you've got and fit it. And the analogy here is, let's say you're cooking an egg. You don't necessarily sit down and do a finite element model of the egg before you start. You just try and cook an egg, and then you kind of iterate and learn from that. So in this case, we've done a few bits of work. The top graphs here basically show how we can map from the voltage curve that we get when we charge a battery, in fact, just a few points on the voltage curve, to estimates of the capacity. So if we do this repeatedly, we can get different estimates of the capacity and estimate what the capacity is without having to fully charge and discharge the battery. And then the bottom curve shows how, if we've got some data from some cells that we've already degraded in the lab, then another cell 3, comes along, and we want to know what it's going to do in the future. And we know that it's being used in a similar way to cells 1 and 2, then we can apply some techniques to extrapolate the future behavior, which is shown here in orange for cell 3. So I'm going to dive into each of these in a little bit more depth in the next few slides. So first of all, the physics-based models. This picture, really nice picture from a paper by Donald Finnegan and colleagues. This shows an X-ray CT scan through a small lithium-ion cell called an 18650 cell. And it's called an 18650 cell because it's 18 millimeters in diameter and 65 millimeters high. And what you can see is this kind of Swiss roll structure inside. So there's almost a meter of electrode rolled up in this thing. And so you can see this layered structure with anode, cathode, separator. And this picture here shows how we can pull out a bit of graphite, some separator, and then cathode on the right. And the cathode's a lithium metal oxide type material. So we can build a model of this central bit, and it looks something like this. So in this model, you can see both a microscale model of the diffusion in the particles, and also a kind of macro scale model just across this slice, which incorporates things like the electrolyte. And this is a little video which just shows, for example, how the concentration of lithium in the electrolyte and the particles is changing as we charge and discharge the cell. Might be interested to know that the Tesla Model S actually has about 7,000 of these cells inside it. So how do we model degradation on top of this? Well, we can put some extra physics in, pick the mechanism that you like, and put some extra physics in to model degradation on top. And in this case, I've chosen to model the solid electrolyte interface buildup on the graphite, which is caused by, well, people think could be caused by solvent reduction. So that's what this cartoon shows. And if you put this all together, you can build a model, and you can do kind of computer-based experiments to see how batteries age over time. In our group, we've been taking approaches like this and trying to use them to improve the performance of real batteries. And here's an example. So let's say I want to trade energy with a battery connected to the grid. What I'm going to do is look at the price of energy over time. So that's what this graph here shows. And then what I want to do is charge the battery when the price is low and discharge when the price is high. And the usual way this works is, if you are taking the view of an economist, for example, is you'd build a fairly simple model of the battery. You treat it like a bucket for energy, and then use that as a constraint, solve an optimizer, and you get a charge-discharge profile, something like this, for example. And you can incorporate some penalty for degradation. So, for example, each cycle costs you some money, and then you'll use the battery less, which is what this middle graph shows. But what we did was we said, well, what would happen if we put in quite a complex physics-based model, and then we'd get the optimization in the bottom. And that's nice, but does it actually make any difference? So we took a year's worth of these profiles, stuck them on a battery tester, and aged some batteries for a whole year. And this graph shows the results, and they're quite interesting. So here you can see the revenue we would have made versus the lost capacity. So the blue one is essentially what happens if we ignore degradation completely. So we make quite a bit of money, but we also lose 15% of our capacity. Clearly that's unsustainable. What's more interesting is the difference between the red and the yellow curve. So the red curve shows a sort of simple linear model with some degradation awareness, and the yellow shows a more kind of physics-based model. And it may look quite subtle on this graph, but there's actually quite a difference in the gradient here. And the physics-based model produces about a 20% revenue increase and a 30% lifetime improvement at the same time. So that's really exciting. But to realize these kinds of benefits in a real system, such as this large system shown down here, it would require much closer integration between the people who put the system together and the cell supplier. And we actually have a spin-out company that's working on this kind of granular control called Brill Power, based here in Oxford. So the final bit I wanted to mention was the more data-driven approaches to understanding battery lifetime. And we might turn to these because actually the physics of battery degradation, really complex, difficult to understand and model. And maybe we don't want to model each of those mechanisms from the bottom up, but perhaps we've got a ton of data lying around. So let's try and fit that instead. So to fit the data, we choose a very simple model in this case. This is just a little electrical circuit model. I won't explain in detail what's going on, but the important thing here is that it has an internal resistance. And that internal resistance is something that we can actually use as an indicator of battery health. Gradually over time, the battery ages, the internal resistance will go up, and eventually that could stop the operation. However, the internal resistance itself is also a function of things like temperature and state of charge and so on. So if we want to try and estimate the internal resistance from data, we actually have to estimate it as a function of a bunch of other stuff. And so we can use techniques from machine learning to try and do this. And we've recently been doing this using data from the field, from small off-grid solar systems in sub-Saharan Africa. So our objective here with our partner Bbox was to try and predict whether we could see whether batteries were going to fail or not ahead of time. So what this video shows is battery voltage on the top over about 2 years of data. And then at the bottom, a prediction of the resistance as a function of state of charge, current, temperature, and time. And if I just run this video, you'll see as we kind of go through the voltage, we kind of learn the shape of these curves. These are, if you like, slices through the surface that I was showing you earlier. And the important thing here is that we've now got a kind of calibrated idea of what the resistance is as a function of time at standard reference conditions. So we can actually use this to build a fault detection algorithm. For example, if we add a threshold, then we could say the resistance has crossed this threshold, so the battery has died. And we've recently demonstrated that we can predict about 2 months in advance with about 85% accuracy when a battery is going to die. Okay, so just to sum up then, some of the near-term issues that we are thinking about over the next couple of years, there are 3 particular things that I just want to mention. The first thing is that a lot of what I've talked about, we've shown that it works in the lab, maybe on 1 or 2 batteries, but actually big systems have hundreds of thousands of cells. And so we have 2 issues to contend with. One is a data management issue, but the second issue is to do with the fact that there's variability between cells. So when you put lots of them in a system, you have to worry about that. Second kind of research angle that we're interested in is diagnostic techniques. We've done a lot of work on frequency domain diagnostic techniques. And so this plot actually shows some analysis of the second harmonic of the resistance, the second harmonic of the current when we inject a large amplitude sinusoid, and we can use this as a non-invasive diagnostic technique. And then the third thing is other types of batteries. So although a lot of our work is on lithium-ion, there is a lot of work going on around Oxford on solid-state batteries, for example, in the materials science department, and we're also interested in things like flow batteries, shown here. So with that, I'd like to thank you all for listening. I just particularly want to highlight my team who've done brilliant work that I've been talking about here, and also to thank some funders, UKRI and Faraday Institution and industry partners. Great.
Well, thank you, David. I assume you can all hear me. And once again, I apologize for the technical glitches that we're gradually ironing out, thanks to the effort of our team. We do have time for a couple questions because we actually have a 15-minute break between now and the next talk. So if anybody has any questions, now's the time to raise them. According to Vicky, there's been no questions on the chat line. I do have a question for you, David. This is sort of related to what you're doing. It's really more of a question I've always had when it comes to batteries and the effect that batteries can have on the environment. And I don't know if you're an expert in this particular area, but maybe you have enough sort of high level sort of exposure to provide some insight, which is, to what extent can batteries be recycled? are there battery types which are more recyclable than others, and is work being done in trying to develop those technologies?
Yeah, excellent question, and really important question as well. Some types of batteries, like lead acid, for example, are very recyclable because lead is fairly valuable. But lithium-ion is economic to recycle lithium-ion at scale. And it might be of interest to people that the things that are particularly valuable in lithium-ion are actually cobalt and nickel, for example, to some extent lithium, but my understanding is it's mainly cobalt and nickel. So that means that certain cathode materials which have cobalt and nickel are, more of a going concern than others. But yes, it's economic at scale is my understanding, but there's still a lot of research to be done. And in fact, the Faraday Institution is running an entire research project on recycling. I'll just say one more thing, which is that quite often when batteries, say an electric car, come to end of life, which is sort of 80% of their initial capacity, they're actually still good to go for many more years. So you could put them into a grid storage facility like shown on the screen here, and just keep using them, perhaps with slightly more limited voltage range. So there's also a second thrust to do with reuse and second life, it's called in the field.
Okay. Well, thank you, Dave. I think we'll call the session to a close. As far as I can tell, there are no questions. The next session starts at 7:25. That'll be session 3. So we have a few minutes to take a comfort break, and I'll see you all again